Bismillah ar-Rahman ar-Rahim. Today we will add more tests in order to investigate convergence of series. The test we have today is called comparison test, or we have two tests, that's why we call them comparison tests. We have the first one, which is called the comparison test. We have another one called limit comparison test. The first one says, assume we have two series, two infinite series, summation n equal to 1 up to infinity of an, and summation of n equal to 1 up to infinity of bn. These series are series with positive terms. Now the test says, if you have an idea about the summation of bn, that is, this summation is convergent. And you know, an is less than or equal to bn for all n. So the terms of the series involving an are less than or equal to the terms of bn. Then the conclusion, then the series n equal to 1 up to infinity of an is also convergent. Simply it says, if the larger one, the series contains the larger terms, is convergent, so the series of the smaller one also is convergent. Keeping in mind that both of them are positive. The second part of the test says, if the series bn is divergent, and we know that an termwise greater than or equal to bn, meaning, if the smaller one is divergent, what can we say about the larger one? Then the larger one also is divergent. So that is what we call the comparison test. I repeat that one. Assume we have an less than or equal to bn, and we have two series, one of them involving an, the other one involving bn. If the larger one is convergent, we can say that the smaller one is convergent. If the smaller one is divergent, we can say that the series involving the larger terms is also what? If the smaller one is divergent, the larger one will be also what? Divergent. That is simply the comparison test. How to use the comparison test, that will be given in the following exercises. Now let us see how to apply this test. Okay, we have a question that says determine whether the given series are convergent or divergent. We start with the given series here. The series from n equal to 1 up to infinity, 1 over 2 to the power n plus 1. Clearly we have terms that are positive. For n greater than or equal to 1, this quantity is positive, so we can apply comparison test. Now what is the idea in applying comparison test? We try to compare the question given or the expression given in the question with something we know. Okay, look for this one. If we just delete this number 1, then it will be a familiar series. That series is the geometric series. So we have an idea about the summation of n equal to 1 up to infinity of 1 over 2 to the power n. We know that this is the geometric series, and we have a test for geometric series directly will give us the answer whether it is convergent or divergent. And we are seeking an idea about or information about the series of 1 over 2 to the power n plus 1. Let us compare these two quantities now. Okay, we have 2 to the n plus 1 clearly is greater than 2 to the power n. That's for any n greater than or equal to 1. So the reciprocals now, 1 over 2 to the n plus 1 is what? Smaller than 1 over 2 to the power n. That's clearly true for any n greater than or equal to 1. This is for n greater than or equal to 1. Always this is holding true. Now, you can call this one bn, call this one an. Does it make a difference here? You may call bn now is equal to 1 over 2 to the n plus 1 if you like, or calling it an. Does it make a difference here? This is less than 1 over 2 to the power n, which is equal to an or bn. Does it make a difference? Okay. Now, what can we say about the series with the summation of an, 1 over 2 to the n? What can we say about that series? Since the summation here, n equal to 1 up to infinity, 1 over 2 to the n, this is convergent, is convergent. Okay, why it's convergent? This is convergent geometric series. Okay, why it is convergent? Since absolute value of r, which is equal to 1/2, is less than 1. That is the criteria for checking convergence of geometric series. This is a geometric series. It is convergent. Why it's convergent? Because the ratio is 1/2 and 1/2 is less than 1. So it is convergent. Now, the contribution of the comparison test says, since we have AN here is greater than BN and the larger one is convergent, so we can conclude that this one also is convergent. So this implies by comparison test, the series given by this n equal to 1 up to infinity 1 over 2 to the n plus 1 is also what? Is also convergent. So that's what we have. So this is one application for comparison test that we apply it for a series that we almost know the answer. This is like a geometric series. Okay, we have adding a constant here, but we can manage to compare it with a geometric series we know. And that series is what? Larger than this, which is convergent. So this one is also convergent. Another example. Let us see this example here. Let's call this one part B that discuss the following question. Says n equal to 1 up to infinity. That is 5 divided by 2n squared plus 4n plus 3. In order to succeed in dealing with geometric series, with the comparison test, it's always recommended to refresh your memory with some famous examples like geometric series, like, for example, the P series, something we know. And we try to compare it with something we don't know here. Okay, if you look carefully for the expression given here, it's like a constant, that's the numerator. In the denominator, this is the more significant term. So it is like constant over n squared. And using our knowledge from before, we know that constant over n squared is convergent, P series. So is this one convergent or not convergent? We try to move in that direction. We try to see if we can compare this with something convergent, as the investigation says, it's convergent. So we need to compare it with something convergent, and the thing we need to find is larger than this. Okay? So if the larger one is convergent, the smaller one is convergent. Let us look carefully for this. If we call this one AN, which is equal to 5 over what? 2n squared plus 4n plus 3. Clearly, this is what? This is smaller than, this is smaller than. What I will do now, I will decrease the denominator. So the value will be increased. So what do we have? I am comparing it with 5 over only 2n squared. If you like, this is equal to 5 over 2 times 1 over n squared. Okay, you can call this one Bn if you like. This is true for any n greater than or equal to 1. Why? Clearly, we have 2n squared plus, this is the justification why this is true, plus 3, this is larger than 2n squared for sure. Okay? 1 over this, 1 over 2n squared plus 4n plus 3 is smaller than 1 over 2n squared. These are positive terms. Okay? And what else we have? We just multiply by 5. So this will be 5 over this is less than 5 over 2n squared. So this is wholly true. Now, what is the benefit of comparing the expression given with 5 over 2 times 1 over n squared? We know from the previous discussion that this is a P series. I mean, talking about the series of 1 over n squared is a P series with P equal to 2, which is greater than 1. So it is convergent. This is the larger one, which is convergent. So the smaller one is convergent by comparison test. Okay, we need to write our answer carefully. We will say since this series, which is n equal to 1 up to infinity, of 5 over 2 times 1 over n squared is convergent. Why it is convergent? Let us write the answer here. It is constant multiple of a P series. It is constant. Okay, let's write it like this. It is constant multiple of a P series with the following property, with our P here is equal to 2, which is greater than 1. So it is convergent because of this reason. Constant multiple of a convergent P series is convergent. Okay, since this is convergent, and since we have, okay, 5 over 2 times 1 over n squared, this is always greater than 5 over whatever we have there, 2n squared plus 4n plus 3, and both of them are greater than 0. This is true for all n greater than or equal to 1. So the conclusion, then we have the following. Then the series given by n equal to 1 up to infinity, 5 over 2n squared plus 4n plus 3 is convergent by what we call comparison test. Okay, so this is the idea how to apply comparison test. We start with a series. Okay, we may have an idea that this series is similar to a P series with P equal to 2, so it's convergent. So we try to look for a series, another series, that is convergent and whose terms are greater than or equal to the terms given by the series in the question. In that case, we conclude by comparison test that our series also is convergent. Okay, more examples will be seen about the test here, comparison test. Okay, let us see more exercises here. Let us discuss part C. Part C we have here is a question like this. It's summation. Okay, we have n equal to 2 up to infinity. And we have here n squared plus 1 all over n cubed minus 1. N squared plus 1 over n cubed plus 1. So, is this series convergent, divergent? How to prove convergence or divergence? The first point need to be done here is to look at an idea, to get an idea about convergence, divergence. This is n squared, this is n cubed. Okay, forget about the constants here. If you simplify cancelling here, assuming we have no constant, this expression behaves like 1 over n. As n goes to infinity, this quantity is similar to 1 over n. Okay, what can we say about the summation of 1 over n? That is very famous. It is a divergence. Either you consider it as a P series with P equal to 1, or you call it the harmonic series. It is the divergence harmonic series. So this gives you an idea that, okay, you may have a divergence series here, because the behavior of this expression is look like 1 over n. And that is divergent, so, okay, this may be divergent, but this is not enough. We need to prove it is divergent. So how to show this? Okay, let's try to do some modification of the expression we have and see what will be gained. I will start with n squared plus 1 over n cubed minus 1. That is our an we have in the question here, okay? And for n greater than or equal to 2, this is positive. Now, if I remove the 1 here, should I get a smaller quantity or larger quantity? I'm decreasing the numerator. So of course this will be larger than n squared all over what? N cubed minus 1. This is for the time being. This is larger than this. But not yet. This is not something we know. It is not something we know. Okay, let's do one more modification. I will say this is larger than. Now if I increase the denominator, then what will happen here? This will be n squared all over, I will add 1 here. So this will be over what? N cubed. I know this is larger than this. If you have a smaller denominator, you have larger value. This is larger denominator, so you have smaller value. Meaning, I have n cubed minus 1 is less than n cubed. So 1 over n cubed minus 1 is larger than 1 over n cubed. Now multiplying by n squared will not affect anything in the inequality. This is n squared over this. This is the proof that this is larger than this. Okay, but now what is this? This is 1 over n. What is the conclusion now? By this, I mean, if you call this one Bn if you like. Now, the terms of an is larger than 1 over n. That's the conclusion. And we know, I will say, since summation of n equal to 1 up to infinity, calling it n or Pn, this is 1 over n. This one is what? This one is divergent. Why it is divergent? This is a divergent either because it is a P series with P equal to 1, or it is the harmonic series. Okay, this is P series with P equal to 1. Okay, so since it's equal to 1, we know it is divergent. So what is the conclusion? This and we have that, and we have summation of, and we have an, which is given in the question, and we have an, which is equal to, okay, n squared plus 1, let's write it down, all over, n cubed minus 1 is larger than bn, which is equal to 1 over n, and both of them are greater than equal to 0, greater than 0. Then, by, let us say, comparison test, what do we have? By comparison test, the series here we have n equal to 1 up to infinity of whatever we have, n squared plus 1 all over what? N cubed minus 1 is divergent. We know that the smaller one is divergent. The smaller one is divergent, so the larger one is also divergent. We are talking about terms which are positive, and we are using what we call comparison test. Okay, more examples to see more types of series only. So comparison test, how to apply comparison test for different type of series. This is the idea of the question. Okay, let us see this nice question. It says, okay, investigate the series n equal to 1 up to infinity, ln of n over n. Is it convergent or divergent? Okay. Ln of n over n. Ln of n times an, let us say. I will tell you that if you are multiplying ln of n by an, and an itself is divergent, then the series also is divergent. If you multiply ln of n by a convergent series, ln of n times an, and summation of n is convergent, then the new series also is convergent. But how to prove this? This is just a sense. How to prove it? You know the logarithmic function here. If you look carefully for the logarithmic function, ln of x, it is equal to 0 at 1, then it will start increasing like this. Okay, this is y, this is the x, this is the y, and this is y equal to ln of x. So what can we say about the given expression we have? Okay, we have an is equal to ln of n divided by n. But you know that ln of n always greater than, okay, let us try to see. This is over n. Now, starting from, let us say this is 1, it is equal to 0. This is 2, let us say this is 3. So exactly at e, the logarithmic function is equal to 1. After e, always the function is greater than 1. So this is always greater than 1 over n for n greater than or equal to what? Or equal to 3. We know that this is true. Okay, let's call this one bn. This is equal to bn. And then, okay, we have only two terms to be removed here. N equal to 1, n equal to 2, n equal to 1, that's equal to 0. Ln of 1 over 1, that's equal to 0 over 1 plus. So this is what we have actually. We have the summation from n equal to 1 up to infinity, ln of n, if you like, over n. This is equal to, okay, summation n equal to, okay, 3 to infinity, ln of n over n, plus the first two terms. At 1, that's equal to 0. At 2, that's equal to ln of 2 over what? Over 2. Fine. So, if this series is divergent, adding a number to a divergent series, that is divergent. If this series is convergent, adding a number to a convergent series, that's also what? Convergent. So what can we say about the series n equal to 3 up to infinity, ln of n over n? Ln of n over n, you can now compare it with ln of n over n. As we said, this is an, and it's always greater than 1 over n, which is equal to bn. This is true for n greater than equal to 3. Now, what can we say about the series 1 over n? The series of 1 over n for n equal to 3 to infinity, this is divergent. Why it's divergent? For the same reason. It is a p series with p equal to 1. So what can we say about the larger one? Of course, both of them are greater than 0. This is greater than 0 and that's greater than 0. Let us say like this. Both of them are greater than 0. Positive terms. The smaller one is divergent, so the larger one should be what? Should be divergent. So that's what we need to write here. Since the summation of 1 over n equal to 3 up to infinity is divergent. Okay, it is the harmonic series or p series, it's up to you, harmonic series, and we know harmonic series is divergent. Okay, so this implies the series we have, which is n equal to 3 up to infinity of len of n over n is also divergent by what we call comparison test. And since this is divergent and this is equal to the summation of these two, of course, a divergent series, if you add to it a constant, the summation is divergence, and this implies the summation from n equal to 1 up to infinity len of n over n is divergent. So these are 4 examples where we applied the comparison test. Actually, we compared the question given with the question we know. I mean, a series we know, either geometric series, p series, etc. If it is divergent, if we need to prove divergence, we need to find a smaller series that is divergent. If we need to prove convergence, we need to look for a series whose terms are what? Larger and convergent. So the smaller one will be convergent. That's basically the idea of applying comparison test. Now I have just a small remark, then we move to another test called limit comparison test. Now before we move to the limit comparison test, I have a small remark about the comparison test. The remark says, be careful here. If an is larger than pn, and these are with positive terms for sure. All our work here with positive terms. And the series Bn is convergent, meaning the smaller series is convergent. We cannot say anything about the larger one. We cannot say that the larger one is convergent. The second one, if An is less than or equal to Pn, so Bn is the larger one and the larger one is divergent. If the larger one is divergent, you cannot say anything about the smaller one. You cannot say the smaller one is divergent. To clarify this, let us look for this specific exercise here. Assume someone needs to compare 1 over 3 to the n minus 1 with 1 over 3 to the n. We know 1 over 3 to the n minus 1, okay, so this is larger than 1 over 3 to the n. 3 to the n is greater than 3 to the n minus 1. So 1 over 3 to the n minus 1 is larger than 1 over 3 to the n. Okay, this series, which is involving 1 over 3 to the n equal to 1 up to infinity, we know it is a geometric series. We know it is convergent. Fine. But this is not helpful. We cannot conclude that the series of 1 over 3 to the n minus 1 is convergent. Why? If the smaller one is convergent, we cannot say anything about the larger one. We cannot say this. So what should we do then? If we have such a case that almost we have a geometric series, but it is not a geometric series. So what should we do? We cannot apply the comparison test. In this case, we have another option. This option is called the limit comparison test. And the test says if you have two series with positive terms, and you know that the limit, that's why they call it limit comparison test. We are taking the limit as n goes to infinity of an over pn. If this limit is equal to c, which is positive, this c is finite, positive real number, then the test says either both series converge or both diverge together. Either both of them are convergent or both of them are convergent. So let us see how to apply the test here in specific exercise. The first exercise here we have says test the series given for convergent, which is almost similar to our question here. Remember, if this question were like 1 over 2 to the n plus 1, we have no problem. We can apply the comparison test. Because always we can compare this one to what? We can compare this one to be less than 1 over 2 to the n, and this is convergent, so this is convergent by comparison test. Both of them are greater than 0. But now the problem, we have minus 1 here. So what should we do? Look for the more significant term in the numerator and denominator. In this case, compare this with Bn, that is 1 over 2 to the n. How to compare it? Take the limit. Take the limit as n goes to infinity of an divided by bn. Okay, let us call all of this equal to an. Okay, so this term is equal to an, and this is called bn. So what is the limit in that case? It is the limit as n goes to infinity. We have an over bn. If you divide an over bn, this is what we have. You have 1 over 2 to the n minus 1 divided by this, so it is multiplied by 2 to the n over 1. So that's exactly what we have. We have the limit as n goes to infinity, 2 to the n all over 2 to the n minus 1. Now you can use Hopital's rule to prove that this is equal to 1, or you can just divide by 2 to the n. If you divide by 2 to the n directly, that will give you the answer. Okay, n goes to infinity. If you divide by 2 to the n, this will be 1. This will be 1 minus 1 over 2 to the n. Now, as n goes to infinity, this goes to infinity. 1 over this will go to 0. We have 1 over 1. This is equal to 1. And 1 is greater than 0. The criteria is very important. We need c to be greater than 0. That's 1 greater than 0. It is finite real number, positive, greater than 0. What is the conclusion now? The conclusion by comparison, by the limit comparison test. Both series will be convergent or both series will be divergent. By limit comparison test, we have the following. Both series, these two series are, the first one is the question itself, n equal to 1, up to infinity, 1 over 2 to the n minus 1. This series and the following series, which is the series we know, n equal to 1, up to infinity, 1 over 2 to the n are, these are both are convergent, both series are convergent, or both are divergent. This is the conclusion of the comparison test. Both series will be convergent or both are divergent. Now, since we know that the summation n equal to 1 up to infinity, 1 over 2 to the n is what? Convergent. Why it is convergent? This is very important here. This is geometric series. This is the reason why it is convergent. Geometric series with what? With absolute value of r, the ratio is 1/2, which is less than 1. Okay? So it is convergent. So what can we say about the other one? Since this is convergent, then the other series, which is n equal to 1 up to infinity, 1 over 2 to the n minus 1 is convergent. Who says this? The limit comparison test. The limit comparison test says both series are convergent or both are divergent. We know one of them is convergent, so the other one is convergent. Let us see more exercises. Let us see one more exercise, at least about limit comparison test. Okay, let us look for the question here that says test for convergence. Test the series given by this n equal to, this is n equal to 1 up to infinity, okay? And then we have here 2n squared plus 3n divided by This is radical of 5 plus this is n to the power 5. Okay? Test this series for convergence. Now, if we look carefully for the series itself and try to get an idea about the series, the more significant term in the numerator is n squared, okay? The more significant term in the denominator as n goes to infinity is n to the power 5, so that is n to the power 5 over 2. If you look for the difference, this will look like, I will not say it's exactly equal to, but it will behave like what? 1 over n to the power 5 over 2 minus 2. 5 over 2 is 2.5, so this is 1/2. So the sense says this series look like it is a divergent series. Why? Because this is P series with P equal to 1/2. So it is similar to a P series which is divergent. So this one is divergent. This is the sense. How to prove it is divergent. How to show it is divergent. Okay. We will do exactly the same. We try to choose our Bn. Our Bn will be chosen to be like this. Okay? We look for the more significant term here, that is 2n squared. Divided by, as we said, the more significant term is n to the power 5, so that's n to the power 5 over 2. Okay, fine. Okay, taking this constant, deleting this constant doesn't affect anything, because at the end of the day we have limit equal to constant, multiplying by another constant that will be, I mean, this is positive constant, so it will not affect anything here. So I can choose my Bn even to delete the 2 here. And I can choose my Bn to be 1 over n to the power 1/2. Radical of n. 1 over radical n. That's in other words, this is what we have. Now let's try to compute the limit now. What is the limit as n goes to infinity of an divided by bn? That's equal to the limit as n goes to infinity of, what is an over bn? This will be multiplied in the numerator, so that will give you the following. It is radical of 5 plus what? This is n to the power 5, and that is, if you multiply upstairs, you have 2 n to the power 5 over 2, plus that will be 3 n to the power 3 over 2. Okay, I'm multiplying by n to the power 1/2 upstairs. Now clearly the limit of this, you can justify this. This is equal to what? Let's try to do it together. If we divide by n to the power 5 inside here, so what do we have is this. We have the limit as n goes to infinity. I'm taking n to the power 5 common factor. So that will be what? That will be 2 n to the power 5 over 2 plus 3 n to the power 3 over 2. Here we take n to the power 5 common factor, so it will be n to the power 5 over 2 outside, and then inside will be what? It will be 5 over n to the power 5, okay, plus 1. What I did, I took n to the power 5 common factor, so this will be 5 over n to the power 5 plus 1, and I took it outside, so it will be n to the power 5 over 2. Now dividing up and down by n to the power 5 over 2, and taking the limit as n goes to infinity, this is equal to 2, which is greater than 0, and it is finite. Conclusion. The limit comparison test says both series, this series and the series of Pn, which is 1 over n to the power 1/2, is either both convergent or both divergent. I repeat. The limit comparison test says both series, which is this series, and the series of 1 over n to the power 1/2 is either both convergent or both divergent. But we know that this is a P series. I'm talking about the summation of Pn. Is a P series with P equal to 1/2, which is less than 1, so it is divergent. So our series is also divergent. Let us write this statement and conclude this exercise. Now, since we have the summation of n equal to 1 up to infinity, 1 over 2 to the power, this is n to the power 1/2. This one is divergent. Why it is divergent? This is P, this is the justification. P series with P equal to 1/2 that is less than 1. So we know it is a P series which is less than 1, so it is divergent. So by limit comparison test, what do we have by limit comparison test? Okay, the given series, the series given by this series given by n equal to 1 up to infinity of 2n squared plus 3 times n divided by radical of 5 plus n to the power 5 is also divergent. So this is the way how to apply the limit comparison test. Now we have the last point is to talk about something called estimating of sums. If we have two series and we are trying to estimate the sums, what can we say about the error of this series? That will be our next point. Now let's come to the last point we have in this discussion. We have estimating sums. It says if the error in estimating the sum of an is Rn, and the error in estimating the sum of Bn is Tn, and we know that Bn is less than or equal to An, then the result says that the error involved is also less than the error involved. And this is very clear if you look for the series we have. Look, we have summation of n equal to 1, up to infinity of an, that's equal to what? A1, A2 plus an plus 1 plus an plus 2 plus etc. And the other one is Bn n equal to 1 up to infinity, and this is Bn, and this is equal to B1 plus B2 plus. This is Bn plus 1 plus Bn plus 2, etc. up to infinity. Now if we said, okay, we will approximate by taking the nth partial sum, so we stop here. This will be called our, if you just move with the same here, this will be called our Rn, the error involved with the estimation by taking only the first n elements, the nth partial sum, Sn. This is called Sn, by the way, and this is called Rn. Similarly, if you estimate the sum here by taking any elements here, so this is your estimate, and of course this will be your Tn, okay? But we know that according to this given here that Bn is always less than or equal to An, meaning Bn plus 1 less than or equal to An plus 1. Bn plus 2 is less than or equal to An plus 2. Bn plus 3 is less than An plus 3. So if you are adding these terms and adding these terms, and this term-wise this is smaller, so of course the summation is also smaller than the summation. Of course, this summation is supposed to be finite because we have what? We have a convergent series. If we have a convergent series, then this summation is finite. Okay, fine. So let us apply it here. The question here says, estimate the error involved in adding the sum of binding the sum of this series with only 100 terms. By adding only 100 terms. What's supposed to be done? Okay, the error involved here, we call it Tn. If we just look carefully for 1 over n cubed plus 1, this is convergent, and this is less than or equal to 1 over what? N cubed. This is always less than 1 over n cubed. So we have An and Bn are positive. One of them is smaller than the other one. So what can we say? Okay, if the error involved in this summation, we call it Tn, then this is less than or equal to the summation, if we take what? If we take only the 100 terms of the second series here, and we know that the error involved here is less than the error involved here. But what is the error involved in Rn? If we take only that summation, which is 1 over n cubed. Okay, this is less than or equal to, you remember we did this one in the integral test and say it is less than or equal to the integral from n to infinity of the function f of x dx. Something like this. Now we need to define a function, so we let our function equal to what? Our function here, f of x is equal to, okay, 1 over x cubed. Our n here, according to the question, is equal to 100. Maybe someone will say, why don't we directly go and integrate this one from 100 to infinity, 1 over x cubed plus 1. Yeah, you can do that, but it is lengthy. You need to pay more time. And you can do it, you can get an idea about the error directly by integrating what 1 over x cubed. It will be more difficult also if the question like this, 1 over n equal to 1 up to infinity, that is 1 over, let us say, n to the power 5 plus 1. Imagine you need to integrate, or n to the power 4, or n to the power 6, or whatever. Integrating from 100 or from n to infinity, 1 over x to the 6 plus 1 dx is not straightforward. If you have n to the power 4, n to the power 4 plus 1, let us say simply like this. This is not straightforward. So what should we do? We compare it with something else that is easy to be calculated. And that's exactly what we did here. We compare 1 over n cubed plus 1 with 1 over n cubed. We know that this is less than this. So the error involving in adding only the first 100 terms of this series is less than the error of evaluating only the 100 terms from that series. And that's the formula we used before to have the answer. And I think it is not a big deal now to calculate this. The integral from 100 to infinity, we call it, this is convergent, of course. This is 1 over x cubed dx. We know that this is convergent. It's equal to the limit as t goes to infinity. Okay? And that is 100 here. To t, and that is x to the power minus 3 dx. We calculate this, so that's equal to the limit as t goes to infinity. And what do we have here? X to the power minus 2 over minus 2. So we can rewrite it like this. It is x to the power 2, x to the power minus 2 over minus 2, and this will be minus 1 over 2, evaluated from 100 to t. And you can show that this is equal to what? That's equal to 1 over 2 times 100 squared. Okay? We can simply evaluate this to be equal to, so our Tn is less than equal to the error Rn, which is less than equal to this number 1 over 2 times 100 squared. That is, this is 100 squared. It is 2, 1, 2, 3, 4, 20,000, something like this. If you multiply by 5, this is 5 over 100,000, something like this. So it is 0.00005. So our error involved in adding the first 100 terms in the series given, which is 1 over n cubed plus 1, will be less than equal to the error involved in adding the first 100 terms of 4 over n cubed, and both of them less than or equal to 0.0005. So this is basically what we have for comparison test and limit comparison test. I summarize. We said the comparison test says if you have an less than or equal to pn, the larger one is convergent, so the smaller one is convergent. If the smaller one is divergent, the larger one is divergent, keeping in mind that both of them are with positive terms. This is one thing. The second one, if the limit of an over bn is equal to constant, which is positive, finite, then both of them are convergent. Both of them are convergent or divergent according to the limit comparison test. Finally, if we have an is greater than or equal to bn, so the error involved in adding in terms of this, call it Tn, is less than or equal to the error involved in adding the same number of terms in the series containing an. That is what we call comparison test, limit comparison test, and estimating sums.